It's a great pleasure to have our next keynote presentation from Trent Jaeger. Trent is a professor of computer science engineering at Penn State. He works on security and system security, as we heard yesterday. He's co-director of the Systems and Internet Infrastructure Security. He has done extensive work on operating systems security and many other areas. And I guess he's also the lead for the CRA on science of security. So we're looking forward to your talk and to the comments you have for our program. Thank you.
Thank you. Thanks for the nice introduction. Thanks for inviting me to speak. The organizing committee. I need to press a button. Huh? It's not the right button. Okay. All right, so I'm going to talk about attack surfaces today. As was mentioned, I work in software security and system security, and what I'm going to talk about is science from the perspective of principles. Can we develop new generalizations for software security, system security that we can leverage to better analyze, better defend our systems, or at least prevent obviously stupid attacks from happening, which we still have some challenges with. So this work was done by a number of my students. In particular, the core of it was done by a student of mine, Hiward Vijay Kumar, who's now at Samsung Research. And so I will talk, I thank him a lot as well. So I had to get this title in, because I was asked to do this talk, and so I thought of a title, and it was kind of pedantic and boring. After being here in Nashville for a few days, I sort of have another title, more related to the problem, which is what do you expect when you left all the doors open, which is how we sort of deploy and develop software these days. We write our software, we put it out there, and there are a lot of ways the software can be attacked, but we don't really pay any attention to that, it seems like, until the adversaries show us the ways that our software can be attacked. And so when we left the doors open for attack, what did we expect, and why haven't we been watching our doors? So as was mentioned, I'm now what's called the consortium lead of this ARL Cybersecurity Collaborative Research Alliance project, which is sponsored and also managed by the Army Research Lab, ARL. And this project involves 18 faculty at 5 universities and 4 researchers at 2 companies, as well as a number of Army Research Lab folks. And so what we're interested in ultimately is developing fundamental science of security topics, as you can see. The focus of the project, though, is mainly on the detection side of things. So the first bullet there, A, about detecting cyber threats, is sort of the core focus. But in doing this, we are aiming to leverage cyber deception, which Kevin talked about earlier. And we're also interested in leveraging machine learning-based techniques, hopefully leveraging them in a way that is robust against the various adversarial machine learning attacks that have been ongoing. And so we have 3 project areas: detection, what's called agility. You can't really read it probably in the bottom there very well, but detection, agility, and what's called learning for deception, which is the phrase that we use for the adversarial machine learning-based techniques, or the applications of machine learning to deception, which is the idea. So the core of the project, as I mentioned, is the deception area. In addition to deception, we're going to utilize moving target and, detection, deception, similar word. Detection is the core. We're going to utilize moving target defense and deception to augment detection, and we're going to see what we can do with machine learning to help us do a better job of detecting threats, possible issues, and and the possible exploits against our system so that we can detect attacks more quickly. So this is a project that has 5 more years to go, so I will come back to this a bit toward the end of the talk related to what we've been doing. So I'm going to talk about science. So science, as we've discussed, has a number of meanings, and so what I'm interested in is sort of science from a little s basic sort of standpoint. How do we extend the scientific knowledge that we have with maybe some new principles that a number of people in the room can utilize effectively? And when you put science in Google, Wikipedia comes up, and it seemed like that was a reasonably useful definition, where they talk about science being a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. And so to me, the key words here are systematic, i.e. there's a way that we all understand to compute this property, and that we can widely apply this, that we can use it to understand what's going on in the real world and perhaps predict what's going to happen next. So ideally we can explain through some scientific principle what's going on in the real world accurately, and ideally more concisely than actually studying everything about the real world. I always want to hit this keyboard down here instead. Okay, so as I said, I work in software security, so what I'm interested in quite a bit are vulnerabilities and trying to detect their exploit. And so I'm going to work from the definition of vulnerabilities, and then we'll get into attack surfaces. So what has often been said is that vulnerabilities can require 3 elements in order for them to actually be vulnerabilities. That there's some flaw, and I'm talking in this case about software, but you could extrapolate it to system configurations or network, but I'm going to talk mostly about software today. So there's a software flaw. This flaw is accessible to an adversary who's then able to exploit this flaw. And so there are these 3 elements. If we're missing any of these elements, there isn't really a vulnerability. If the adversary can't exploit it, there's not a vulnerability. If the flaw isn't accessible to the adversary, then they can't exploit it. And so our goal in the project is to detect intrusions that exploit vulnerabilities, ideally even previously unknown ones. So we'd like to come up with some principles that would help us to assess systems to detect vulnerabilities that we haven't seen before. Now, I think we talked about this a little bit yesterday in the panel, but the way that the community, the research community, myself included, and I'll talk about a specific case study as we've decided to call them today, is that vulnerabilities are treated in a fairly ad hoc manner in research. There's a specific system, there's a specific configuration of the system, there's a specific type of vulnerability, or many types of vulnerabilities, and so we learn about these individual vulnerabilities and how they might be exploited and how they might be, these exploitations may be defended, but to much of an extent, it's hard to extrapolate on these individual pieces of knowledge. It's hard to correlate these attacks across or the defenses even across these individual pieces of work, so that we can then build on it and deploy something that we can all then depend on to prevent certain types of attacks and then build on this. And this is a challenge we face in the software and systems community. So I was talking to Pete Lascoco here at the break, and we were talking about, say, SE Linux, and we knew about reference monitor concept, in the early 70s, and so to actually get something into, commercial systems that would implement something that was, getting at the reference monitor concept in a way that was closer to the original principles in commercial systems, took, over 30 years. To get canaries, stack canaries from the paper publication into a particular system, and stack canaries is a very trivial technique to prevent buffer overflows, took like 10 years. So there's a challenge about how to speed up this overall process of getting technology into systems. So I'm going to talk, as I mentioned, about a particular case study now, and then I'll come back to the science part and the extrapolation in a little bit. So bear with me. Hopefully this will be a little bit fun. It's an attack paper, so it's got to be fun. hopefully there are some broader things we can draw on it rather than just the attacks themselves. At least that's the aim. But, so the idea here is we are going to talk about an attack first and the implications of that with respect to defense, and then the principles that we might want to enforce to prevent this attack. And so you might consider, say I'm from Penn State, a university, so we have some maybe university web server. And in a university web server, lots of people can deploy web pages in this web server and get those web pages served by the web server. And they each have their own directories that only one individual has access to. Whoops. And, but what one can do is set up, say, a symbolic link from their directory or a particular file in that directory to another file that they might want to access that they wouldn't normally have access to. I'm using Etsy password here as an example. I mean, Etsy password is something that everybody can read, but you could imagine instead the web server's private key, say, or maybe a more privileged file that's accessible to the web server here. So I have a little video even, so what's happening here, if you can see, is we're going to configure our bad guys' configuration of the web server by setting the error document to serve this particular file, 404.html, which is pretty standard. But instead of actually serving a particular file, when an error occurs when you're trying to retrieve a web page from this directory, we're going to create a symbolic link to this Etsy password file that we want to gain access to instead. And so if you just type in a web page that doesn't correspond in a particular directory that doesn't correspond to, or a URL that doesn't correspond to an actual web page, you'll be served the error document instead, which is the password file from the web server. So as I tell the students at Penn State, you shouldn't do this kind of thing without asking for permission first. Because that is actually the password file that was on the Penn State web server. So what happened? So what we have is the notion that we have a web server, and a web server can access a bunch of files. So it might want to, it's a web server, it might want to serve web pages, so we do that. And when we serve web pages, as we discussed, we'd like to actually serve web page files, but not serve the, things like the password file or the private key of the web server. But the web server also does authentication. And in that case, the web server should use the password files and this sort of information. And in theory, also should not use web pages, right? We don't want somebody putting a web page in that's crafted like a password file, so that might be used to do authentication. So we have this other problem as well. And so the challenge is that the program here, this web server, received a resource that wasn't expected for the particular purpose that it had at that particular time. And so we have these little daemon guys, that's the untrusted party, and then the little shield refers to the protected or privileged resource. And so an adversary may either trick the web server into using adversary-controlled files when we really want a privileged or protected file, or vice versa, may access, as in the case of the password attack I showed you, access some privileged file that we didn't want it to access when we were interacting with the adversary. So these attacks have been around a really, really long time. These are the kind of stupid attacks that we'd like to see go away. I think a fellow named McPhee I've seen cited first referred to these kind of attacks back in 1972. And Matt Bishop wrote a really elaborate, detailed paper about these kind of attacks in about 1995, I think. And there have been a number of defenses, but currently we still lack a coherent approach to dealing with these. But the basic problem is that the adversary controls what I'll call bindings or links to the that are used during the name resolution process when you're trying to retrieve a file. And the victim can take the adversary can take advantage of this to redirect the victim to a file of their choosing. And I will show you an example here where the adversary controls, sorry, I should have explained this first. The adversary controls this, has the write privilege to this var mail directory, and so the adversary can create this file called root, for example, and instead of creating a file called root, they can create a symbolic link that refers to this resource that they want to serve instead. And also this attack has been studied a lot because it's kind of tricky. There are various race conditions. So even if the victim is trying to check, that var mail root is really a file, the adversary can, due to a race condition, change that to a link between the check of the file and between the actual opening of the file. So the victim can be redirected still to the resource that was unexpected, even though they were looking for it. If they're not looking for it quite the right way, they can still be attacked. Alternatively, the other case is called a file squatting attack. Again, the adversary has the ability to write to var mail, and they can create a file in advance for the victim that they control, and they could then serve adversary-controlled content through this root file that they control instead. And so both these file squatting and these link traversal style attacks are possible. So what's causing this sort of problem, and how might we actually get to the bottom of dealing with this and other kinds of stupid attacks that we still allow on our systems? And so a challenge is that we have, the way we deliver software these days is that we have a combination of folks that are all working together to get your software deployed and running on your systems, which is all good. It makes it easier for you guys to get your software running, makes it easier for them to do their work to get the functionality there, but causes problems. So we have our programmer, and the programmer writes the code. So the programmer writes some program, and it has these three, say, open system calls or library calls at the bottom. And the programmer thinks about what kind of attacks they might have. And the programmers may not think about this at the level that we would like. But they might know, most of them would know, for example, that the temp directory, if it's going to use the temp directory, that you're going to interact with other parties. You share the temp directory with everyone, and so some other party might provide some files in the temp directory that are unsavory and that might cause these kinds of attacks. And so the programmer can add defenses, or in this case does add defenses, to protect their program against accesses using the temp directory. But they may assume that accessing the configuration file and the web pages will be okay because they're defined by the server. But the administrator here on the left might configure the application program so that through the configuration file to choose a place for the web pages that can be written by untrusted parties, and the access control policy is defined by the OS distributor. And again, to enable this functionality that people might want, they give access to untrusted parties to write to these directories used to retrieve HTML files as well. And so this creates a problem where there's a mismatch between the programmer and the OS distributor and the administrator. And so this mismatch, in this case, led to the problem that we've seen. And you'll see that there are several other problems out there that have been out there for a long time that are based on this sort of mismatch. So if we go back to the definition of vulnerability, what we see is that this attack really is caused by the middle part, by the accessibility. In this case, the programmer didn't think there was going to be any problems, so they didn't add any defenses. And so once the accessibility was provided, the exploitation was quite straightforward. So an answer, we might think, is, well, why don't we put defenses, just put defenses everywhere and defend every time we access these resources. And the challenge is that the defenses themselves are complex to add and maybe even more importantly, expensive. Apache, which is I think what this code here is based on, had this defense implemented on their web servers, but that you could turn it on and off as an option. And so in the time we were working on this a few years ago, the Apache documentation explicitly said something to the effect of, for better performance and for no symlink protection, select this option. And so that meant basically that people, if I read this, I would assume, hey, better performance and this no symlink protection as well, so that would be good. So I would accept that option. But that meant turning the defense off, essentially. So they've changed that now, but in the past they had guidance basically to turn off the defense. But the defenses are complex and expensive. And so just to check for races themselves, part of the attack, you have to check for the existence of symlinks, and this code actually prevents using symlinks, which may prohibit some functionality that people use. You have to look for race conditions. You have to look for what's called inode recycling, so you can actually create enough inodes to cycle the number, the count, inode count all the way back around to have a different inode have the same number as one that was checked previously. And you have to do this for each of the directories used in the name resolution process. And so this is a slow and error-prone method. And in addition, it doesn't actually prevent all of the attacks that we've talked about. And so programmers are loath to add this sort of defense to their programs. And so this is a challenge that we face in the sense that the programmers will only add these defenses when there's some reason for this, and the reason usually is an exploit occurred rather than some systematic reason. Okay, so what I'm going to talk about a bit now is the attack surfaces. And so attack surface, I don't know, the first that I'm aware of attack surface was the use by Michael Howard at Microsoft in around early 2000s. So if you remember at this point, Microsoft was having some major security problems where one vulnerability enabled you to take over the internet. And so they started trying to look at security, and this is one of the principles that they started thinking about, was this notion of an attack surface, where the idea is that your program, system, network has entry points where an adversary might supply input, and these places where the adversary may interact with your host or your program are things you should look at, you should track. And so we're going to talk over the course of this talk about whether this is something that we can make as a principle that we can work from as a community. Now, the early use of attack surfaces wasn't very profound. Partly this was due to the nature of the Microsoft Windows products at the time, because if you, some of you are fairly young, but in 2002, the Microsoft Windows systems that were running pretty much were wide open. Every service was turned on, was accessible to the network, and they ran as admin. So basically, if you had one vulnerability, you could take over the whole internet. And that's what people did through various worms that came about in the early 2000s. Even at IBM Watson, in the security research group that I worked in, I worked with some people who were pretty hardcore security folks who also watched their own systems fairly carefully. And I remember when, I think it was SQL Slammer hit, it compromised one of my colleagues' systems because his system was running the SQL server because Microsoft just turned everything on whether you used it or not. And so his system was compromised as well, much to his chagrin. So at this point, attack surfaces were fairly large, and what Michael Howard basically argued at this point was that reducing the relative attack surface was a good idea, but this was a start, but only the first step. And what we saw over the course of the next 10 years, for example, now switching to Linux, was the emergence, for example, of hosts protected by what's called mandatory access control. One of the, if you're not familiar with mandatory access control, one of the key features of mandatory access control as it was applied was to restrict the permissions of these network-facing services so that they did not have permissions that would enable you to compromise the host with one vulnerability. So they would, in a sense, confine these network-facing services. In addition, of course, we had seen a number of attacks over these years, and services themselves, network-facing daemons, have been hardened in a number of ways, but this was mainly through a penetrate and patch sort of approach. So those of us who've been talking about design for security for many years weren't too happy about this approach to improving security. And then the OS distributors did do changes to the configuration of their systems to reduce the attack surface in the way that the Microsoft folks talked about initially with the attack surfaces. So after we did all of this, then what happened is that we got to where I described just a little bit ago, where we have this attack and there's still this possibility of mismatches because we have programs that are taking these unforeseen risks. So let me talk a little bit about how we detect these things, and then we'll come back to preventing them. So, we did some work on building an analysis tool to test programs for these problems, to understand basically how prevalent these sort of mistaken attack surfaces were in existing Linux systems. And so the fundamental problem, basically, as I've alluded to, is that if adversaries can write to a directory that's used when you're resolving the name of a file to an inode, that an adversary can redirect your access wherever it wants. And if you're not watching for it, then it's pretty much game over. So what we did is we built a tool, and it would try to emulate this adversary behavior. Let me show you. So we'd have our program that we're testing, this victim. It would ask to request a file. And so then the tool, which ran in the kernel at the time, would find out what directories were going to be used in the name resolution, determine whether an adversary could access any of those, and then change the file system to reflect what an adversary might envision, and then let the system call return to the victim and see what the victim did. And if the victim used the descriptor associated with the file that we gave them that was connected to this malicious target instead, adversary chosen target, that we would find that this is an attack, record it as a vulnerability. We could roll back the namespace, give them the real resource that they wanted instead of the one that was chosen by the adversary, so the victim could keep running and keep doing what it was supposed to do, and we could see if there were other flaws as well. And so, we ran this over Linux systems as various applications in Linux, and what we found is that about on a Fedora and Ubuntu, about 5% of the name resolutions that are done were involved in a situation where there was an attack possibility, where the adversary could interfere with the name resolution process of these programs. And as you can see, about 10 to 20% of the name resolutions that we saw were vulnerable. That is, the programs themselves weren't expecting these problems and they did not defend against them. And so, you know, it's less than 1% of the total name resolutions, but that's not very heartening. Still, it's still a significant number. And so, for example, here a list of the problems. So there were 21 unknown vulnerabilities that were detected for these 19 programs, number of which were system programs being able to attack root programs. There's some old and new programs. There's some programs that had CVEs already reported, but that were still vulnerable to this problem. The vulnerabilities hadn't been fixed in that particular deployment. Some pretty old programs like the printer daemon, for example, had these. And then also the third from the top, the startup scripts. Ubuntu had just gone to the trouble of rewriting a number of their startup scripts, and it turned out a lot of the rewritten startup scripts had these kind of flaws. They just finished them months before. So there are a lot of the latent issues of this type, and so we also looked across the Linux services to see what the extent of the problems were with respect to the breadth of the attack surface for Linux services existing on the system. So basically we looked at a number of system programs you would think of that ran on Linux, and we computed based on the mandatory access control policy what files, for example, or what resources those programs would run that could be written to by an adversary. And turned out that about 13%, only about 13% of the individual library calls, the individual places in the program where it retrieves a resource, where referred to resources that could be adversary modified. So this is, in some sense, not a huge number. And if we look at the third column from the left, only 81 points in these programs actually did overt operations like reading and writing resources. And so these are the operations where it's most likely that an attack would occur. This student, he did a survey basically manually looking at CVEs to see how the CVEs correlated with the individual points in the attack surface, and he found manually about half of them corresponded to known CVEs. And so you can see that this sort of penetrate and patch approach to managing systems seems to be the way we were going about it, because almost every one of these, almost half of the entry points he found had CVEs behind them. And so there were issues that had to be detected through penetrate and patch, or through vulnerabilities being reported. So that's sort of from the attacker perspective. So let's look a little bit at what the defenders do. What do the programmers do? How do they defend these attack surfaces? So in this case, we looked at file retrieval vulnerabilities also due to the input being received by the programs. So there's another problem that we have when we retrieve files. That is that the file name may be built from input that we receive from external programs. And so this input could be benign, where you ask for a web page and the web server uses that to build the file name and retrieves the file for you. But of course there are some other flaws that may allow the adversary to specify input, use it to build file path names that might lead to files that the adversary isn't supposed to have access to, such as, again, our friend the password file here. And so both of these attacks relate to our challenge of protecting these attack surfaces. And so what we find here is we're looking at the expected attack surface that the programmers are defending on the left, and the attack surface that the deployment is giving us on the right. And so what we expect is that the program's expected attack surface is going to be a superset of the deployment's attack surface, right? So the program is defending at least the number of attack surfaces that are going to be provided or made available by the deployment. And so in this case, we're looking at, on the left-hand side, say at R3 we have, R3 to R4, we have a defense for receiving the input to build the file name, and then a defense for resolving the file name. And we expect that at R4, both of these defenses are present so that we can protect ourselves from attacks due to the adversary input. So anyway, what we did was we looked at a number of programs, and we found in this column here, these are the number of entry points that are not defended by the program. And so SSH, OpenSSH defended over 80% of the interfaces, which is fairly unusual, whereas all the others had at least 55% of the entry points were not defended. And so again, the programmers are waiting for these attacks to occur before they add the defenses. And OpenSSH is somewhat of a special case anyway, because it was privilege separated and retrofit to deal with some security problems, which is not the case with these other programs. Although Postfix is a fairly specially built program with security in mind. So we built a representation of the flows from the particular, so this is a graph showing library calls that the program makes. And each of these library calls may either receive input that's used to build a file name or may open a file. And then the edges refer to the level of filtering, where the dark edges mean that there are defenses. So you can see defenses are fairly sparse here. And in the upper right corner, there are cases that are not defended, where there's attack surface that's not defended in this case, where the program's not expecting attacks, but the system deployment allows these attacks to occur. Okay, so that's sort of the history and examination at a high level of how we looked at attack surfaces and how they haven't, you can see that there were a number of latent vulnerabilities related to us not tracking attack surfaces systematically. You can see that the programmers haven't really done a systematic job of defending these attack surfaces. And so here I have a set of lessons. So what we're seeing is that as you deploy your programs and you deliver them, and they live for years and years and years and years, there's the possibility that unexpected attack surfaces may emerge that enable pretty straightforward attacks to be performed against your program that you didn't expect when you wrote the program in the first place. Second, the programmers don't really have any systematic way of assessing the implications of the attack surfaces that they've created and how these attack surfaces have evolved over time. And so pretty much we've been limited to this sort of penetrate and patch approach rather than a proactive approach. And finally, if you have an attack surface, there's a good chance that it's going to be attacked. So you should have an understanding of what your attack surfaces are and have defenses for that. And this comes from a set of papers, mostly the first 4 here. So now I'm going to broaden the discussion and talk about what does this have to do with security, a science of security. And so I'm going to talk about a few thoughts and give you some notion here of where we may go with this. But what I'd like to do is argue that this notion of attack surfaces is something that we should keep track of. So historically, I mean, we've published a number of papers, a lot of people have published a number of papers, either looking for flaws in programs or looking for ways to exploit programs. And flaws and exploits, as I mentioned at the beginning of the talk, are both fairly ad hoc, right? There are many, many different types of vulnerabilities, many different types of ways for them to be, many types of flaws, many types of ways for them to emerge. And so it's hard to correlate them across individual systems, individual programs. So what we see is a challenge where our research is specific to these vulnerability types, and then even the vulnerability types reoccur in different system deployments where we might think, oh yeah, that vulnerability has already happened, right? Someone deploys a new type of system, but we see often the same kinds of vulnerabilities emerging. And so how might we deal with those? So we're hoping for science that where we have principles that apply broadly, and the challenge is that things like vulnerability types and individual ways that these vulnerability types manifest themselves across different system deployments is a difficult thing for us to apply broadly. So what do we need to do to look at attack surfaces as something that we can apply broadly? So as we discussed at the beginning, the science requires us to have something systematic. We need to be able to compute this. I think we can, we've talked about being able to explain vulnerabilities with this technique, but we also need to be able to predict new types of vulnerabilities across many deployments and many vulnerability types. So in terms of systematic, thought is that we can then compute attack surfaces in an easier way across systems than trying to deal with computing specific flaws. So the claim is that we can compute a conservative but accurate attack surface in a fairly straightforward way. And so one of the papers in the readings refers to this integrity wall approach, where what we do is take a conservative approach for what an adversary is and compute, for example, the subjects that we must trust, and everybody else is an adversary. So in that paper we talk about subjects with privilege, with access to particular kernel resources that would enable you to compromise the system, and if those are available to a subject, then you must trust them. And if a subject can write your code, then you must trust that subject as well. And so this enables us to compute a fairly conservative adversary model, and that was the adversary model used in the experiment that showed about 13% of the entry points were adversary accessible. So we actually only have a modest level of attack surface to defend typically in these programs, smaller than I expected. And then in terms of identifying entry points, in the past we did a runtime analysis, but with available hardware now, such as Intel PT, we can actually collect information about what resources are accessed at what entry points in a fairly straightforward way, low overhead, and fairly automated, since the hardware will help us compute this rather than you having to run things manually. And then in terms of tracking what attack surface is used, whether someone is expanding, is trying to access adversary-controlled resources in a new place in the program, this can be detected fairly efficiently, we found in a study that we did in HoTSoS a few years ago on this process firewall project. So in terms of managing where your threats are coming from, we have shown that we can do this sort of thing. In addition, once we compute attack surfaces for individual programs, we can then use these for motivations to try to write and improve security of our software over time. So a challenge is that right now we don't really have a good idea of where we're going to face particular problems. We don't know that much where to put energy into things like fuzz testing. And so, so here, identifying that about 10–15% of your entry points are the ones that are going to receive untrusted input can hopefully enable us to focus with more confidence on dealing with the various types of problems that we face here, classified at a high level as memory errors, information flow errors, and the last one, the system calls, is the one we've been talking about. The idea might be that if we know that we're going to receive input at a particular point in the program that's untrusted, we could then use this to drive making sure that if we do an unsafe operation from that point forward, that we should look at maybe trying to make that into a safe operation. If you have pointers, for example, that are dependent or can be tainted by adversary-controlled input, you might want to make sure that you don't have pointers that that are possibly going to exceed bounds, or have what George Nekula called wild pointers, which could point to fairly arbitrary places in memory. You'd like to ensure that these are safe accesses. Finally, in the CRA project, we're looking at this, as I said, science of security related to detection. And so we have a project on intrusion detection that we're starting, where attack surfaces are sort of the first line of reasoning about intrusions. So I don't know how well you can see that up there. I can read it okay from here, so I'll go ahead with it. But the first step in task 1 is about predicting the attack threats, and that's essentially the attack surface problem. So we need to figure out where threats are coming into our system as a first step in trying to assess how we're going to track adversary behavior. And there are two aspects. One is in terms of attack surfaces, we want to, from attack surfaces, detect the flaws and exploits, or at least track our system from these attack surfaces and understand where flaws and exploits may emerge. But also, related to what Kevin was talking about earlier, we may, from a deception standpoint, also, if we can understand the attack surface, we can also reason about how we can expand the attack surface in order to do deception and try to identify adversaries more quickly in this detection space. And so both of these dimensions are driven by this notion of understanding what the attack surface is and utilizing that as a principle for guiding our management of defenses. So to conclude, we've seen over the years, I'm sure you've all seen that vulnerabilities are caused by many factors, but one of the key factors, and maybe we haven't been paying enough attention to this, is the notion that the adversary must have access in the first place, and that we don't really track where this is, where the adversary may have access. It's relative to these other aspects of flaws and exploitation. Identifying where an adversary may have access is a more straightforward thing to do. So in this talk, I've been advocating us focusing on the idea of leveraging attack surfaces as a basis for managing security. So our proposal is that we can compute them systematically and track these relatively effectively at runtime, as well as use attack surfaces both to help hopefully make our software stronger, as well as to expand the ways that we detect attacks through, for example, deception techniques. So I'm happy to take questions you have now. So thanks.